James Webb just found galaxies that shouldn't exist. The universe isn't following the rules we know. The universe isn't just mysterious. Right now, it's showing us that we don't fully understand it. Even top scientists must rethink everything. Adam Rice, a Nobel Prize-winning physicist, discovered dark energy, the invisible force pushing galaxies apart faster across the universe. Now the James Webb Space Telescope is revealing something stranger. Numbers that don't just challenge one theory, they challenge all of cosmology. At the heart of this crisis is the Hubble constant. It measures how fast the universe expands. Right now, not a billion years ago or later. Measuring it seems simple. Point a telescope at a galaxy, find its distance, measure its speed, and divide, but the universe refuses. For decades, measurements were rough. Some astronomers said the universe was 10 billion years old, others 20 billion. The numbers hid deeper secrets. Then in 1998, two teams discovered something extraordinary. The universe's expansion isn't slowing. It's speeding up. Dark energy appeared. Reese LED, one team, Pro Mutter, the other Schmidt, was part of Reese's team. All three shared the Nobel Prize for discovering dark energy. Cosmologists folded dark energy into Lambda-CDM. 68% dark energy, 27% dark matter, 5% normal matter for 30 years. Then precision arrived. Reese's team measured Cepheid stars, the cosmic distance ladder, and found a number that didn't match predictions, sparking a mystery. Reese's team used Cepheid stars to measure galaxy distances. With unmatched precision, the results shocked the scientific community. At the same time, another team used the cosmic microwave background to predict today's expansion rate. Their number didn't match Reese's measurements. The difference is small, 73 versus 67, but with precise measurements on both sides. This 8 to 9% gap is huge. It's called the Hubble tension. For decades, scientists hoped it was a mistake. Maybe a telescope error, maybe a miscalculation. But every check confirmed the gap was real. Webb Telescope solved a major question. Were Cepheid stars distorted by crowding? No, Hubble's measurements were accurate, and the ladder was solid. Reese's team rejected the crowding hypothesis at 8 sigma. That's less than a 1 in 100 trillion chance. The discrepancies. At the same time, Webb discovered galaxies in the early universe that shouldn't exist. Too massive, too bright, and too organized for their age. One galaxy, nicknamed the Big Wheel, had a full spiral structure, less than 2 billion years after the Big Bang, impossible by standard models. The data didn't match predictions. Either galaxies formed their mass in place rapidly, or an unknown process funneled gas in a remarkably orderly way. A team found 300 candidate galaxies that are brighter than models allow. If confirmed, our understanding of early universe structure needs a major revision. Webb sees the universe in high definition for the first time. We can separate stars clearly, even in crowded galaxies millions of light years away. Reese's team calibrated Cepheids with Type I supernovae to measure faraway galaxies. Every rung of the ladder confirmed the high expansion rate. Hubble and Webb numbers agree. The crowding problem was real for Hubble, but barely an issue for Webb. The measurements are solid. The team rejected the crowding explanation at 8 sigma, less than a 1 in 100 trillion chance. That error caused the Hubble tension. Webb also revealed early galaxies that formed too fast, too massive and too bright. Our models can't explain how they got there so soon. The Big Wheel galaxy had a fully formed spiral, less than 2 billion years after the Big Bang. Standard cosmology says this shouldn't exist yet. Either these galaxies form mass in place extremely fast, or some unknown process organized huge amounts of gas early. Neither fits the standard model. Some early galaxies turned out to be powered by black holes, rather than stars. Webb revealed a new class of objects called little red dots. Simulations suggest stars may have formed in violent bursts. In the early universe, galaxies caught mid-burst look much brighter than their total mass. Even if some early galaxies are smaller than first thought, their existence shows star formation back then operated differently than in the later universe. The Hubble tension and early galaxy problem are connected. Both challenge Lambda-CDM, the same model predicting expansion and galaxy formation timelines. Locally measured expansion doesn't match predictions from the early universe. It's the same framework under pressure from two directions. Some think the solution is subtle. Maybe dark energy changes over time, stronger in some eras and weaker in others, affecting expansion. But research shows expansion matches Lambda-CDM, back to the cosmic microwave background. If there's a break, it's in the universe's earliest moments. Theorists explore exotic ideas, extra dimensions, new particles, or unknown physics in the first moments after the Big Bang. Some propose particles that existed only briefly, adding a pulse of energy that sped up expansion. Others question gravity's behavior on cosmic scales. Simulations suggest early stars formed in sudden, violent bursts caught mid-burst. Galaxies appear brighter and more massive than they really are. Even with partial explanations, Webb shows the early universe is different. Our old models assumed it behaved like today, but it didn't. New instruments will join the search. Webb Roman and Vera C. Rubin Observatory will vastly expand the data on supernovae, dark energy, and galaxies. We've only scratched the surface. The path is clear. These discoveries mark the start of a new chapter in understanding the universe. Every major leap in physics started this way. We built instruments precise enough to see where our models break. Newton's mechanics worked until Mercury's orbit didn't fit. Einstein's relativity worked until quantum physics conflicted at black holes. Lambda-CDM has worked perfectly for 30 years. Now cracks are showing, but not because scientists were wrong. Webb collects photons that left their source billions of years before Earth existed. These carry information we don't yet know how to interpret. The gap between what we expected and what we're seeing isn't a failure. It's evidence of a universe deeper than we imagined. Rees and his team confirmed Hubble's numbers were correct. Measurement errors are ruled out. The universe itself is refusing to cooperate. Early galaxies formed faster and more violently than expected. Star formation back then may have followed rules, unlike anything we see today. Some early galaxies appear massive and organized, defying models. Even partial matches raise new questions about cosmic evolution. Upcoming observatories will massively expand our view, mapping dark energy, dark matter, and galaxies billions of light years away. And maybe that's the point. We're not failing, we're outgrowing the map we drew. The universe is deeper than we realized. The universe doesn't arrange itself for our convenience. For 13.8 billion years it existed before anyone tried to understand it. Webb is capturing light that traveled billions of years. Each photon carries clues about the universe we don't yet understand. Early galaxies grew fast and violently. Star formation back then didn't follow the slow, steady patterns we see in today's universe. Even if some early galaxies aren't as massive as first thought, their behavior shows that early cosmic physics was different. The Hubble tension and early galaxy problems converge. Both pressure Lambda-CDM from different directions, revealing cracks in our understanding. Dark energy, first discovered decades ago, still drives the expansion, but new measurements show its effect, maybe more complicated than we imagined. Type I supernova help measure distances, confirming the cosmic ladder. Every rung supports the higher expansion rate observed locally. Webb images reveal galaxies that shouldn't exist yet. Their mass and brightness challenge the timelines predicted by standard models. Some galaxies form spirals in a fraction of expected time. Either mass formed rapidly in place, or unknown forces organized them early. The universe isn't breaking. It's showing us how deep and complex it really is. We're witnessing the start of a new chapter in physics. Every discovery pushes the limits of our models. Webb shows galaxies forming faster and brighter than anyone expected. Cepheids and Type I supernovae remain crucial. They confirm distances with high precision, ruling out simple measurement errors. Some early galaxies are too massive and organized for their age. The Standard Model's timeline is under pressure from multiple angles. The Hubble tension isn't small. Precise measurements reveal an 8 to 9% gap between local expansion and early universe predictions. For decades, researchers assumed a subtle error caused the discrepancy. Webb confirms the measurements are real, leaving theory under pressure. Simulations suggest early star formation may have occurred in sudden bursts. Caught mid-burst galaxies appear far brighter than their total mass. Some galaxies formed spirals too soon. Either mass built rapidly, or unknown forces organized enormous amounts of gas early. The physics of the early universe may differ from later times. Webb forces us to rethink assumptions hard-coded in previous models. Webb captures photons that traveled billions of years. Every new observation challenges what we thought we knew about cosmic history. We may have misunderstood the universe, not because we were careless, but because it is far more complex than we imagined. Webb lets us see the early universe in incredible detail. Galaxies appear massive and structured far sooner than models predict. Distance measurements from Cepheids and supernova confirm high expansion rates. Simple errors cannot explain the Hubble tension. Some galaxies form spirals and dense clusters early. The timeline for structure formation is compressed, defying expectations. The Hubble tension persists. Locally, we measure 73, while early universe predictions are 67 kilometers per MPC, a significant and real gap. The solution may require exotic physics, evolving dark energy, extra dimensions, or new particles in the universe's first moments. Early star formation may have occurred in violent bursts, making galaxies appear brighter and more massive than their actual total mass. Galaxies like the Big Wheel form spirals too early. Either mass accumulated rapidly, or unknown processes organized gas efficiently. Webb shows the universe was more active and dynamic early on. Old assumptions about steady formation no longer hold. Each photon carries information from billions of years ago. Decoding them will rewrite our understanding of cosmic history. This isn't a failure of science. It's the sound of discovery, seeing the universe beyond the limits of our old maps. Webb has shown us galaxies forming in ways we never imagined. The universe is behaving differently from our models. Distance measurements are precise. Every rung of the cosmic ladder supports a higher expansion rate than predicted. Some galaxies are massive, bright, and structured. Early standard cosmology struggles to explain how they formed so fast. The Hubble tension persists. Local measurements show 73. Early universe predictions show 67 kilometers per MPC. A real discrepancy. Theorists explore evolving dark energy, extra dimensions, or unknown particles in the first moments of the universe to explain these gaps. Stars in early galaxies may have formed in sudden bursts. Mid-burst galaxies look brighter and more massive than they truly are. Some galaxies form spirals too soon. Either rapid mass buildup or unknown processes organized gas efficiently in the early universe. Webb is rewriting our understanding. The universe back then was more dynamic and extreme than we had assumed. Each photon from distant galaxies carries secrets from billions of years ago. Decoding them will transform cosmic history. We may have misunderstood the universe not because of error, but because it is far more complex and far more amazing than we realized.
Thanks for watching. For more amazing space facts, subscribe to Planet Facts and don't forget to hit the bell icon to stay updated.